Let's now go through machine problem number 2. The first task simply asks you to load data to the MATLAB and Python workspace and then save the data to time and force variables. These time and force variables are what you use to plot and show the normal and parallel forces involved in a jump, which is what you did in task number 2. In the video, you were shown just one jump, but in this graph, there are 3 jumps. The mechanism is the same in each of the jump. In task 3, you are simply asked to ask the user for the limits of integration. In task 4, you needed to find the indices corresponding to the limits of integration. You then use these indices in task 5 to replot the graphs so that what is seen are only the most relevant parts of the graph, which are the parts that we need to integrate over. In task 6, you are finally asked to integrate the data using Simpson's 1/3 rule. Now let's discuss the solution in more detail and compare between MATLAB and Python codes as well. As you will see in the implementation of Simpson's 1/3 rule, knowledge of these differences will be crucial. Let's go back to task 2. The only thing that I want to highlight here is the difference in the syntax in the function subplot. In MATLAB, we see that the number or rows and columns and the position of the particular plot are separated by commas. No commas are needed for Python. Going to task 3, where you ask the user for input, the syntax is precisely the same. However, in MATLAB, the command takes in a number by default. If you want the user to input a string, you add an option to the input command like so. This tells MATLAB that whatever the input is here is transferred to lower limb as a string. In Python, however, the input by default is a string. This is why we needed to convert the string to an integer first, using the int command, before we are able to use the variables lower val and upper val. This allows us to use these variables as indices for the time and force variables. If we did not use an int command, Python will return an error message. Now let's go to the main task of implementing Simpson's 1/3 rule. It's important to determine whether the number of data points being considered for integration is even or odd, as you will see in a bit. First, let's discuss how this is implemented in MATLAB. In MATLAB, the lowest index allowed is 1. Let's consider this representation of the dataset where n equals 9. The numbers you see represent the indices of the data points. So the first row represents the first addend in the expression for the integral. The second row represents the second addend in the expression for the integral. Since n equals 9, then n minus 1 equals 8 and n minus 2 equals 7. The sum can then be easily implemented. But what if there are only 8 data points, that is, n equals 8? What you do is to implement Simpson's 1/3 rule to only n minus 1 data points, which in this case is n minus 1 equals 7. After obtaining the sum, simply add the value of the nth data point. One more thing you should factor in is that the step size for the index in the for loop must be 2. As you can see from this example, the index in the first iteration is I equals 1. In the second iteration, it's I equals 3. And in the third iteration, it's I equals 5. And so on. Thus, the step size must be 2 in the for loop. Let's take a look at how this is implemented in MATLAB. First, I determine whether the total number of data points is even or odd from this command. The 2 here means that I am dividing the length of these variables by 2. So if m equals 1, then that means I have an odd number of data points and MATLAB executes this set of commands. Otherwise, if m equals 0, then I have an even number of data points and MATLAB executes this set of commands instead. You can also see that the step size is introduced between the variables lower val and upper val and the 2 semicolons. If n is odd, then the for loop terminates at n minus 2. But if n is even, then the for loop terminates at n minus 3. Furthermore, if n is even, I add the very last term to the resulting sum. We see that I wrote down exactly the same set of commands twice. This is where creating a function becomes useful. I will now create a new function which I will call mySimpsons with fn or fp and h as input variables. I already prepared this in advance, and here is the function. This function takes in as input data and h. This line determines the number of data points by determining the length of the data, and then it determines whether the number of data points is even or odd. The if-else command executes a set of commands depending on whether the condition m equals 1 is satisfied or not. So if we go back to our live script, we only need to call on the function twice. This makes this program more efficient since we use less number of variables and process steps. Now let's consider how this is implemented in Python. In Python, the lowest index is 0. Thus, in this representation of the dataset where n equals 9, we have indices from 0 to 8. The numbers you see represent the indices of the data points. So the first row represents the first addend in the expression for the integral, and the second row represents the second addend in the expression for the integral. Now here's the problem when it is implemented. If we check the length of Tn from I equals lower val to I equals upper val, we get 8. In MATLAB, you get 9. What makes things a bit complicated in Python is that the lowest index starts from 0 and it only counts one less than it should. So here it didn't count Tn upper val. It does not include the last data point. So this is why when I solve for the modulus, I should add 1 here so that the last data, Tn upper val, is included. Now when we go to the for loop, it's perfectly fine to write the upper val here, because this range function will not include the upper val index anyway. Like I said, it doesn't include the last digit or the last number. We can check this by doing this. As you can see, it only sums up to 4 terms and does not include the upper val, which is equal to 23, which is what we expect. Finally, we create a function that will solve for Simpson's 1/3 rule in Python. I already did that to save time. I also call the function mySimpsons with input data and age. When I call on the mySimpsons function, I need to include the last data point in the limits of integration. In order to do that, I have to add +1 here. Let's now interpret the data. If we consider the range from 1.5 milliseconds to 5 milliseconds, we get this result in MATLAB. For the normal force, we see a slight dip at around 2.2 milliseconds before it starts to go up at about 3 milliseconds, after which the force becomes negative between 3 and 3.5 milliseconds. At 3.6 milliseconds, it goes up again before going back down slightly below 0 at 4 milliseconds, after which it goes back to 0. First, why is the normal force 0? That's because the platform was reset to 0 value while the person was standing on the platform. So if he moves out of the platform, such as when he is in the air, we see a negative force, which corresponds actually to his weight. That's what we see between 3 and 3.5 milliseconds. The dip at around 2.2 milliseconds and 4 milliseconds corresponds to a slight loss of contact between his foot and the platform as his knees are bending. The maximum force at 3 milliseconds is the push before the jump, and at 3.6 milliseconds is the first contact on the plate after the jump. Let's go to the parallel force. If you watch the video again, you'll see that the plate actually moves forward and backward. That's because the person is trying to maintain his center of gravity above his feet. However, as he bends his knees, his center of gravity slightly moves and his feet adjust forward and backward in order to keep them directly under his center of gravity. That's what you see in the parallel force. I hope that you've learned a bit more about the complexities of programming. As a final note, I'd like to introduce you to another advantage of using MATLAB's LiveScript and Jupyter Notebook. In MATLAB, We can move the output in line with the code, like so, by pressing this button. We can also remove the lines of code by pressing this button. Now you can hand in this report for your other physics classes, for example, by saving this as a PDF file, or as a Word file, or as other types of files. If exporting doesn't work, you can print this to file. You can do the same for Python and save your program as a PDF file, which you can submit to your teachers. I hope you've learned more new things in this video. At this point, I congratulate you for having completed 2 topics. The next few topics will be challenging, but I hope you find them interesting and useful as well.